In a previous chapter, we discussed about measuring the relationship between two characteristics or variables of a population based on paired samples collected on those variables. A good measure of relationship between two variables is given by coefficient of correlation, which tells us about the strength of relationship and the direction of relationship as well. After determining the correlation between two variables, we wish to determine a mathematical relationship between them so that we can predict the value of a variable based on the value of the other variable and explain the impact of changes in the values of variable on the values of the other variable. Fitting a mathematical function between two correlated variables using paired observations on them is studied in regression analysis. For mathematical convenience and ease, we fit a linear relationship, and in this presentation, we discuss how to fit and analyze a regression model. We also discuss a generalized case of regression model when we have many variables affecting the values of one variable. Before proceeding, let us have discussion about dependent and independent variables. Out of the two variables, one is considered as a dependent variable and the other as independent variable. Using regression model, we study those changes in the values of dependent variable that are resulted by the changes in the values of the dependent variable. Actually here, we study those changes in the values of dependent variable that are resulted by the changes in the values of independent variable. Here is the printing mistake. Or in other words, we regress the dependent variable on the independent variable. So the dependent variable is also called as the regressed variable or study variable, while the independent variable is called as regressor variable or explanatory variable. Suppose we have two variables, x and y. If x is the independent variable and y is the dependent variable, then y is a function of x. Sometimes it is quite clear which one of the two variables is regressor and which one is regressed. For instance, out of rainfall and yield of a certain crop, rainfall is independent variable which affects the yield of a certain crop. So yield becomes dependent variable. In some situations, it depends on the study. For instance, out of demand and supply, if you wish to study demand as affected by supply, demand becomes regressed and supply becomes regressor. You have to take the other way in case you wish to study the supply as affected by demand. After discussing about dependent and independent variables, now let us come to the simple linear regression model. A linear regression model between a single study variable and a single explanatory variable is termed as simple linear regression model. That means here there is only one study variable and one explanatory variable. Study variable is the dependent variable, explanatory variable is the independent variable. Of course, at the end of this chapter, we discuss the models having a single study variable and many explanatory variables. Such models are termed as multiple linear regression models. Now, let us denote the study variable by y and explanatory variable by x. We collect paired observations x1, y1, x2, y2, etc., xn, yn on the variables x and y. These observations are plotted in a scatter diagram as shown here. X on x-axis and y on y-axis. In this figure, the various dots together constitute the scatter diagram. The simplest relationship between x and y is a linear relationship which is given by y equal to a plus bx. Fitting a model means obtaining the values of the intercept term of the line A and the slope of the line B on the basis of collected observations on x and y. Different values of A and B will give different lines as shown in figure. And this line is for a particular set of A and B, and this line is for another set of A and B, and this green line is for another set of values of A and B. That is why here it is written different values of A and B will give different lines as shown in this figure. How to obtain the most suitable or the best values of A and B is a question which is discussed now. For that purpose, we take the help of this least squares estimation. To obtain some reasonably good estimate of A and B, we use the method of least squares, and it helps us the most in studying y as affected by x. If you see this figure, we fit a line y equal to a plus bx. The exact relationship between x and y is not linear. We are only approximating the relationship by a line. Therefore, it is not correct to write the line equation y is equal to a plus bx. We write it as y bar is equal to a plus bx, where y bar is the predicted or fitted or estimated value of y. The exact relationship between x and y can be written as instead of y equal to a plus bx, we write y equal to a plus bx plus error. The error in this equation is shown here. If you see this point, from this point to this line a plus bx, this much is the difference, and from this point this is the difference, and from this point this is the difference, from this point this is the difference, from this point this is the difference. So that way error is present. Error is present. This error is the difference between the observed value and the predicted value of y. Using collected observations x1, y1, x2, y2, etc., these errors or residuals can be written as yi minus a minus bxi for I equal to 1 to n. We wish to have such values of a and b for which these residuals are minimum. Obviously, we want these errors to be minimum. In least square method, we minimize the summations of squared residuals. For this, we differentiate sigma I equal to 1 to n yi minus a minus bxi whole square with respect to a and b separately and equate the derivatives to 0. Solving those two equations, we get the following estimates of a and b. This a cap, that is estimate of a, that equal to y bar minus b cap x bar, where b cap is the estimate of b. This is given by sigma I equal to 1 to n xi minus x bar multiplied by yi minus y bar by sigma I equal to 1 to n xi minus x bar whole square. And this numerator is written ssxy and denominator is written as ssx. This ss stands for sum of squares. The values of a and b obtained using least square method are called as least squares estimates of a and b. That means this a cap and b cap, these are called the least square estimates, LSEs, of a and b. Also, the relation between the correlation coefficient r between x and y and LSE of b is given as this r equal to b cap multiplied by square root of these terms, and this we can write here as b cap multiplied by square root of ssx by ssy. Thus the signs of r and b cap are the same. This is the relation between the correlation coefficient r and this estimate of b. Now let us try to understand this by means of an example. In this example, we have 15 observations. That means small n equal to 15. This example is related with watching television also reduces the amount of physical exercise, causing weight gains. A sample of 15 10-year-old children was taken. The number of pounds each child was overweight was recorded. A negative number indicates the child is underweight. Additionally, the number of hours of television viewing per week was also recorded. These data are listed here. So here the TV watching hours is given in this row. How many number of hours the children watched. And this overweight in here it is given in pounds. Here this is given in pounds. So here the overweight is 18 pounds, here 6 pounds, 0 pounds, and here -1 means it is actually underweight, and overweight is 13 pounds, 14 pounds, and here underweight is 9 pounds, here underweight is 7 pounds. What we have to do is fit the regression line and describe what the coefficients tell you about the relationship between the two variables. Now we make this table. And here, which one is steady variable and which one is explanatory variable we have to identify. And in other words, which is dependent variable, which is independent variable, we have to find out. Here, dependent is variable is overweight. So dependent variable overweight is written as YA here. And independent variable, that number of hours of watching the TV, that is here. That is written as XI. So then we are calculating this. From these values, we are calculating the average of X as 31.4667. And from this column, we are calculating the value of Y as mean value of Y as 5.7333. And then what we have done is Xi minus X bar. That means this 42 minus 31.4667, that is 10.5333. 34 minus 31.4667, that is 2.5333. Then 25 minus 31.4667 minus 6.4667. Like that we have done these calculations, Xi minus X bar. And similarly we have done Ya minus Y bar. That how it is done, you see, 18 is the value of Y1 here, minus 5.7333. That is 12.2667. Then 6 minus 5.7333, that is 0.2667. This way we have calculated, and Ya minus Y bar values are put in this column. Then what we have done is we have squared this Xi minus X bar, and in this column we have multiplied Xi minus X bar with Ya minus Y bar. That means this column and this column, these are multiplied and values are given here. And then this summation of this last column, that is giving us SSXY, that is 649.8667, and this column, that is summation of this Xi minus X bar whole square values, that is giving us SSX. So SSX is 671.7333. Now using this calculation, we have this estimate of B, SSXY by SSX. If you want to have a relook, you can see here that estimate of B is SSXY by SSX. And by substituting those values, we are getting B cap as 0.9674 and A cap as Y bar minus B cap X bar, and that is 5.733 minus 0.9674 multiplied by 31.4667, that is minus 24.709. This Y bar value is here. Y bar is 5.7333 here at the bottom. So we have substituted that value here. So we have got Y, finally this equation as Y cap, that is equal to minus 24.709 plus 0.9674x. This Y cap is the estimate of Y. Estimate of Y is now given as A plus Bx, where A value is minus 24.709 and B is 0.9674. So that is drawn here. The number of hours of watching TV, that is on the x-axis, and then overweight is shown here and underweight is shown here below, and this is plotted, and this straight line that is the equation minus 24.709 plus 0.9674x. So predicted Y, this y cap is also now called predicted y. And this shows the scatter plot, and the value b cap 0.9674 is the change in the value of y for a unit change in the value of x. And the intercept is a constant, or the value of y when x is 0. The fitted line can be used to predict some value of y for a new value of x, but that new value of x should be within the range. It should be within the range. For example, the predicted value of y when x equal to 30, then we will substitute the value of x as 30 here in this equation. Then y, the predicted value of y will be minus 24.709 plus 0.9674 multiplied by 30. So that is coming as 4.301. So 4.301, that means weight gain for 30 hours of TV watching per week is 4.301 pounds. This is the estimated value of the weight gain. It is advisable to predict y values for those x values which are in the range of the collected samples, as the behavior of the data may be different in future and past. Now let us come to the coefficient of determination. When the actual relationship between observed x and y values is almost linear, the fitted linear model will be a reasonably good approximation of the actual relationship. In case the actual relationship is not linear, the fitted linear model may be misleading. The quantities yi minus a minus bxi are called as residuals. For a good model, the magnitude of all the residuals should be as small as possible, because they are the errors. Therefore, these residuals can be utilized to tell us something about the goodness of the fitted model. For that purpose, studying y using x means explaining the variability of y using x. And here, what is done, the variance of y values is 1 by n, sigma I equal to 1 to yi minus y bar whole square. And this is partitioned into two parts, as shown here. 1 by n sigma I equal to 1 to n yi minus y bar whole square is written as 1 by n sigma I equal to 1 to n. And here one yi cap is subtracted, and here yi cap is added, so that this remains the same. And however, due to this way of writing, we can write this summation equal to 1 by n sigma I equal to 1 to n yi minus y cap whole square plus 1 by n sigma I equal to 1 to n yi cap minus y bar whole square, or this way. Now it can be shown that the product term is 0, this product term, 1 by n sigma I equal to 1 to n yi minus yi bar multiplied by yi minus yi cap multiplied by yi cap minus y bar is 0, since yi minus yi cap is the residual, and the quantity sigma I equal to 1 to n yi minus yi cap whole square is called as sum of squares due to error, SSE. The quantity sigma I equal to 1 to n yi cap minus y bar whole square is called as sum of squares due to regression, SSR, as it is the part of the variability of y, which is explained using regression model. Thus, total variability in y, that is called this SST, that is 1 by n sigma I equal to 1 to n yi minus y bar whole square. This is equal to SSY, is partitioned into two parts: explained variability SSR and unexplained variability SSE. That means explained variability is indicated by SSR, unexplained variability is indicated by SSE. And this SSE is this sigma I equal to 1 to n yi minus y cap whole square. And SSR, that is given here, sigma equal to 1 to n yi cap minus y bar whole square. So this is the relation, SST equal to SSR plus SSE. The fraction of SST explained by regression is given by R square. So R square is expressed as SSR by SST. That can be written as 1 minus of SSE by SST. It is clear that the R square value lies between 0 and 1. When SSR is closer to SST, then R square will be closer to 1. Here you can see that when SSR, as R square is defined as SSR by SST, when SSR is closer to SST, then R square will be closer to 1. This means that regression explains most of the variability in Y and the fitted model is good. That means R square value equal to 1 means the fitted model is good. When SSE is closer to SST, that means when SSE, this SSE is closer to SST, then R square will be closer to 0. That means here you can see if SSE is becoming closer to SST, this term will almost approach 1, then 1 minus 1 will be 0. So when SSE is closer to SST, R square will be closer to 0. This means that regression does not explain much variability in Y and the fitted model is not good. That means R square is equal to 0 means fitted model is not good. The quantity R square is called as coefficient of determination and is used to evaluate the goodness of the fitted model. For simple linear regression model, coefficient of determination R square is the same as square of the correlation coefficient between X and Y. Correlation coefficient between X and Y, that is already I had shown by small r. So here for simple linear regression model, coefficient of determination R square is same as the square of the correlation coefficient between X and Y. Here you can see from this figure, for this R square is here R small r, that is correlation coefficient is minus 1 and here it is decreasing and here it is increasing. So for R is equal to 1, this is positive correlation and here the negative correlation, and in both the cases R square is equal to 1. R square is equal to 1 means the regression explains most of the variability in Y and the fitted model is good. This model is good as well as this model is good. This model is for positive correlation and this model is for negative correlation. Now if we take this figure, here R square can take any value between 0 and 1, this figure as well as this figure. But if you take this figure, here R square is 0. R square approaches 0 in this case. So R square is equal to 1 means a perfect linear relationship between X and Y. In these models, 100% of the variation in Y is explained by X. And here in this figure, as I have explained in figure 14.4p, that indicates relatively weak linear relationships. In this case, some but not all of the variation in Y is explained by X. And in this figure, R square is 0, which means no linear relationship. In this model, none of the variation in Y is explained by X. So this is our common conclusion. When R square is equal to 0, then none of the variation in Y is explained by X. Now for the same problem which we have seen as example 14.1, now this part is related to obtaining R square for the model fitted in example 14.1 and comment on its value. So for that purpose what we have done, yi values are written, then yi cap, these are predicted values, a plus b cap xi, these are given here, and then this yi minus yi cap whole square, and here this column is yi minus y bar whole square. This is done for all 15 students. This table is, in fact this table is continued here also. This table is continued here also. And then based on these values, of course we have taken this column summation, and this is SSE equal to 190.2216 and SST, which is nothing but the summation of these values. of yi minus y bar whole square, that is 818.9333. Thus r square is equal to SSR by SST. That can also be written as 1 minus SSE by SST. By substituting these values, we are getting r square value as 0.7677, which is close to 1. Thus, the fitted model is considered to be a good one. Now, let us come to the standard error. All the observations of a data set cannot be exactly the same as their arithmetic mean. Variability of the observations around arithmetic mean is measured by standard deviation. Similarly, in regression, all y values cannot be the same as predicted y values. Variability of y values around the prediction line is measured by standard error of the estimate, which is given by SYX. SYX is called standard error of the estimate, and that is given by square root of SSE by n minus 2. When the predicted values and observed values are close, then standard error is small. However, standard error is not a very good measure of judging the goodness of the fitted model. It should be considered along with coefficient of determination and other measures that are to be discussed later. What are the assumptions or conditions required? The relationship between x and y is almost linear, as we have seen now. Our coefficient of determination is also 0.7677, which is closer to 1. There is no meaning of approximating a non-linear relationship by a line. You can see here this figure. Here actually it is showing some non-linear type of relation. There is no meaning to fit to a straight line for this. Similarly, here also you can see it is some non-linear type of relation. There is no meaning to fit a straight line. And now coming to this figure B, it shows the linear relationship. This figure as well as this figure. Errors or residuals are statistically independent. This can be made sure by collecting a random sample, that is, independent pairs of observations in the sample. And now you can observe this figure. Residuals are shown along this vertical line and x values along the horizontal line. And this one, figure 14.6a, though here one can get the idea, these are not statistically independent. Residuals are not statistically independent in this figure as well as in this figure. But here in this figure, figure 14.6b, we can say the residuals are statistically independent. And as I said, this figure 14.6b, we see that the scatter plot between residuals and x values when the errors are independent or uncorrelated, to be more precise. The assumption of independence can also be examined using Durbin-Watson statistic, which is given by d equal to sigma I equal to 2 to n ei minus 1 whole square by sigma I equal to 1 to n ei square, where ei is yi minus a minus bxi, are residuals. The value of d lies between 0 and 4. When it is nearer to 2, residuals are uncorrelated. For positively correlated residuals, d approaches 0, and for negatively correlated residuals, it approaches 4. In practice, a value of d between 1 and 3. Even though ideally speaking, we say that d value should be closer to 2, but in practice, a value of d between 1 and 3 is usually considered to be accepted. All the errors have a common variance, and that is called homoscedasticity. When all the error variances are not the same, we have heteroscedastic models. Such models are fitted using some advanced method. Here you can see this figure 14.7a, this figure as well as this figure. These come under heteroscedastic models, whereas this figure 14.7b, that errors have a common variance. So these can be said as belonging to homoscedasticity models. Now let us take another example. Obtain the standard error of estimate. Actually, we are continuing the first example only and the various additions we are making to that problem. Obtain the standard error of estimate and examine the assumptions of linearity, independent errors, and homoscedasticity for the model fitted in the first example. The solution is standard error of estimate is SYX, that is given by square root of SSC by n minus 2. As we have already calculated SSC value, substitute here. N is 15 observations. So, standard error of estimate is 3.8252. And the standard error can take any positive value. Now, assumptions. Assumptions, linearity. The scatter plot of the data is presented, which suggests almost linear relationship. Here, if you see, x values are shown here along this x-axis and residuals are shown along this y-axis. And we can observe that there is almost linearity is present here. So the scatter plot of the data, yes, here, this is the scatter diagram between x values and residuals. So, except to the one outlier, like this point is called outlier, this is much away. Except this outlier, all other data points are satisfying the linearity assumption. So then second assumption, independence. And from this figure, it is clear that the given data satisfies the independent errors assumption. If we calculate Durbin-Watson statistic D, by substituting these values, we are getting this D value as 2.6726. And the value of D is closer to 2. This implies uncorrelated residuals. As we already discussed, the D value between 1 and 3 is accepted. And while the values of 0 to 1 and 3 to 4 are alarming. And here we have got the Durbin-Watson statistic value as 2.6726. It is closer to 2. Thus the residuals are almost uncorrelated. This is what we want actually. Then homoscedasticity. And from this figure and from the previous figure 14.3, we can observe that homoscedasticity of the model is good and it is verified. Now testing the hypothesis about the slope and correlation coefficient. For that we are going for a t-test for the slope. In this model y equal to a plus bx plus error, if b is 0, then the model cannot be considered as a linear model. If b is 0, then y equal to a plus error. Therefore, here we test null hypothesis. We take it as b equal to 0 and alternative hypothesis we take as b not equal to 0. The test statistic is this, Tc equal to estimate of b cap by square root of SSE by n minus 2 multiplied by SSX. And by substituting those values in this case, for the same example 14.1, if we test the hypothesis that the slope is 0 against it is not 0, then we have test to statistic value as 6.5546 at 5% level of significance and 13 degrees of freedom. How this 13 degrees of freedom we have obtained? Here already it is mentioned that students t-distribution with n minus 2 degrees of freedom. N is 15, so 15 minus 2, that is 13. So for 13 degrees of freedom at 5% level of significance, critical value using t-distribution is 2.16. We can see the t-distribution table from the statistical tables. From there we can observe this value as 2.16. But now the calculated value is 6.5546. So as per our hypothesis testing procedures, we have to reject the null hypothesis and accept the alternative hypothesis. And here rejecting the null hypothesis means here, that means b is equal to 0, that is rejected, and we are going for alternative hypothesis, b is not equal to 0. Therefore, at 5% level of significance, we reject the null hypothesis and conclude that there is an evidence of linear relationship. Now we can conduct F-test also. F-test can also be used as an alternative to T-test for linearity. Here also we test the null hypothesis B is equal to 0 against alternative hypothesis B not equal to 0. And this test is based on the concept of partitioning the total variability SST into explained variability SSR and unexplained variability SSE. And on the previous pages we had already discussed the formula of obtaining this SST, SSR and SSE. After obtaining these sums of squares, we make following Anova table. This is the Anova table. Regression are explained, that is indicated by SSR. Residual are unexplained, that is indicated by SSE. Degrees of freedom for this regression are explained variation, that is 1. And unexplained, the degrees of freedom n-2. And total degrees of freedom n-1. The sum of squares, here this regression are explained, that is SSR, residual are unexplained, that is SSE, and total is indicated by SST. Now mean sum of squares, that is, now mean sum of squares is SSR by degrees of freedom. Here degrees of freedom is 1 only, so SSR by 1, that is equal to SSR. And now coming to this mean sum of squares, that MSE is equal to SSE by this degrees of freedom n-2. So this. And then what is F ratio? F ratio is calculated as this MSR by MSE. And if we apply this F test to our first example, continuing that first example, test the hypothesis that the slope is 0 against it is not 0. That means null hypothesis is B is equal to 0. Alternative hypothesis is B not equal to 0. In our case, the degrees of freedom 1 here, degrees of freedom n-2 is 13, total degrees of freedom 14. And here sum of squares, that is SSR value, and here 190.2216 is SSE value, and 818.9333, that is the SST value. Then MSR, that is 628.7118 by 1, and mean sum of squares 190.2216 by 13, that is 14.63243. Now F ratio is calculated as this 628.7118 by 14.63243. So we have got F ratio value as 42.96702. Now if we see the F distribution table, the computed test statistic 42.96702 at 5% level of significance and 113 degrees of freedom. The critical value using F distribution can be found as 4.67, which is smaller than the computed value. That means our calculated value is more than the table value of F. So from that we conclude that this null hypothesis is to be rejected and the alternative hypothesis is to be accepted. Alternative hypothesis is accepted means at 5% level of significance we reject the null hypothesis and conclude that there is an evidence of linear relationship. That way the linearity can be tested using T-test or F-test. Now T-test for correlation coefficient. And for that we have this equation, T-test for correlation coefficient. And when the variables x and y are linearly correlated, it is meaningless to fit a linear regression model between them. Therefore, we may like to examine whether there is some significant linear relationship between x and y or not. Here we wish to test the null hypothesis correlation coefficient between x and y is 0. And the alternative hypothesis correlation coefficient between x and y is not 0. The test statistic is given by this, where smaller is the correlation coefficient between the sample observations of the variables x and y. Now, the same problem if we continue here, and test the hypothesis that the correlation coefficient between this number of hours of TV watching and overweight of the children is 0 or not. The null hypothesis we have taken as correlation coefficient between x and y is 0. Alternative hypothesis we have taken as correlation coefficient between x and y is not 0. And when we correlation coefficient in sample values we have calculated by this, then test statistic by substituting the value of correlation coefficient r 0.80162 and n value as 15, we have got test statistic 6.5550, and at 5% level of significance and 13 degrees of freedom, the critical value using t distribution is 2.160. From the tables we can find this, and as the calculated value is more than this tabular value of 2.160, we reject the null hypothesis. That means at 5% level of significance, we reject the null hypothesis and conclude that there is a significant correlation between the variables. Now let us discuss about the confidence interval estimate of the slope. The point estimation of the slope b is given by the least squares estimate, b cap equal to ssxy by ssx. A confidence interval estimate of b at a given confidence coefficient 1 minus alpha can be obtained by this: b cap plus or minus t alpha by 2 with for degrees of freedom n minus 2 multiplied by square root of sse by n minus 2 into ssx. And confidence interval estimate of slope b is not much used in practice. And if we calculate this confidence interval estimate of the slope for this example 11.1, that construct a 95% confidence interval estimate of slope b for the model fitted in example 14.1, and we can see for 95% confidence, that means alpha value is 5%, so 1 minus alpha is 95%, and degrees of freedom 13, because n number of observations 15, so n minus 2 degrees of freedom, that is 13. Critical value from the t distribution table is 2.160 as shown in the previous example. So therefore 95% confidence interval estimate of slope b is given by this, by substituting the values b cap plus or minus that t value 2.160 for the given degrees of freedom multiplied by this square root of mse by ssx. So this is the interval now, confidence interval estimate of the slope 0.6486 and 1.2862. Now coming to the confidence interval, the weight gain for 30 hours of TV watching per week is estimated as 4.301 pounds in one of the previous examples. This is a point estimate of the population mean of Y population at a given X value. We can also obtain the confidence interval mean or mean response at some given X value as yi cap plus or minus t value for a given degrees of freedom n minus 2 and for the given level of confidence sxy multiplied by the square root of 1 by n plus xi minus x bar whole square by ssx, where xy is given as square root of sse by n minus 2. This is the standard error of the estimate. Here you can see in this figure, the upper line represents the upper confidence limit and lower line shows the lower confidence limit. And in the middle line, green line, that represents the predicted Y values. And now the prediction interval. Using confidence interval, we estimate the mean value of Y or mean response, which is a parameter. In order to predict the individual value of steady variable or the response for a given X value, we obtain prediction interval. Please see that this prediction interval is for the individual value of the steady variable. And that is given as this: yi cap plus or minus t value for the given degrees of freedom and a given level of confidence R significance, and SYX multiplied by square root of 1 plus 1 by n plus xi minus x bar whole square by SSX. Now if we want to find out this 95% prediction interval of overweight for x is equal to 30, then simply substitute the values, that yi cap, that is 4.301, and plus or minus the t value at 5% level of significance, 2.160. 5% level of significance means 95% confidence, multiplied by this SYX value, that is 3.8252, and then square root of 1 plus 1 by 15 plus this xi minus x bar whole square, that particular value 2.1511 by 671.7333, or here plus or minus is given, so by when we do that interval, if we take plus we get one value, if we take minus we get another value. So here this interval is shown as minus 4.2452 to 12.8472. Now let us discuss the use of MS Excel for this simple linear regression. We can use data analysis tool pack in MS Excel, and here the summary output for this particular example is shown here. This is obtained using MS Excel facility, and the summary output you can see here: regression statistics, multiple R square, adjusted R square, standard error, observations, like this. And multiple R is the correlation coefficient or the square root of our coefficient of determination, capital R square. And R square, in words it is written, it is actually our capital R square. Adjusted R square is of no use in simple linear regression model. It will be discussed later in multiple regression models. Then standard error. This is the standard error of the estimate, that is written here. And observations, number of observations 15 in our first example. Then coming to the Anova, here you see the regression and residual, and number of degrees of freedom 1 here, and residual number of degrees of freedom n minus 2, that is 13, and total 14. And here SS values are written and MS values are written, F value is written. And if you compare this with one of our that F test, you can observe here, that is nothing but this, like this. That regression, SSR, residual, SSE, total SST, and those values are 628 point something, 190 point something, total is 818 point something. And mean squares, mean sum of squares, that is MSR, that is SSR by this degrees of freedom 1. So SSR by 1, that is SSR. And MSE is SSE by n minus 2. So the same thing, and here F ratio is 42.96702. The same value you can see here. And the significance here, this is written as 1.83945 multiplied by 10 to the power of minus 5. In fact, this is called the p-value of the test. And since it is less than 0.05, so the null hypothesis is rejected, and we conclude that there is an evidence of linear relationship. So here the value, if this value is less than 0.05, then null hypothesis is rejected and alternative hypothesis is accepted. And our alternative hypothesis is that there is evidence of linear relationship. And continuing the MS Excel output, here you can observe here the intercept coefficient and this TVX, that coefficient. These are actually the least square errors of intercept and slope. And then standard errors of least square errors. These standard errors are given here. And computed t statistics for intercept and the slope. Here if you remember the 6.5549 we calculated as a t statistic. I show you in one of the previous pages. Yes, here. This is 6.5550. And here. And this is coming to our t-test for the slope here. T-test for the slope, then the test statistic value is 6.5546. And this value, that is for the correlation coefficient. The 6.5550 is for the tested statistic for correlation coefficient. And now, if we go to this Excel sheet, here you can see that computed t statistics for intercept and slope here 6.554. Then p values are written here, and p value for intercept and slope both are below 0.05. Here you see this is 0.0002. Here it is actually 0. These values are less than 0.05. That means slope is the null hypothesis is rejected and alternative hypothesis is accepted. Null hypothesis is that the slope is 0, but now as null hypothesis is rejected, slope is not 0 and intercept is not 0 as well at 5% level of significance. Then these are the intervals, lower 95% and upper 95%. These values, if you remember, 0.6486 and 1.2863. 0.6486 and 1.2863. If you see here, 0.6486 and 1.2863. Here you can observe here 0.6486 and 1.2862. This is the confidence interval estimate for the slope. So that is what written here. Confidence interval estimate of intercept and slope. These two values 0.6486, 1.2863, this is for the slope, and minus 34.9666, minus 14.4515, that is the confidence interval estimate for the intercept. And yes, a scatter plot between x values and residuals used to verify the assumptions of linearity, homoscedasticity and independence, that is shown here. Now by this we complete the simple linear regression where there is one dependent variable y and one independent variable x. But now let us go for multiple linear regression model. In simple linear regression analysis, we fit linear relation between one explanatory variable x and one response variable y. In some situations, the response variable y may depend on more than one explanatory variable. For example, cost of certain item may depend on labor cost, electricity cost, and raw material cost. Salary of a person may depend on his or her education and experience. Sales of certain item may depend on cost and advertising expenditure. Suppose that the response variable y depends on k number of explanatory variables denoted as x1, x2, etc. The linear relationship of y as a function of x1, x2 up to xk can be written as y equal to a plus b1 x1 plus b2 x2 plus etc. plus bk xk plus error. The above model is called as multiple linear regression model. In this model, a is the intercept or constant term, and then b1, b2, etc., bk are called as regression slopes or regression coefficients. In order to fit this model, we need to estimate the regression coefficients and the constant. A is the constant, and B1 to Bk, they are the regression coefficients. For this, we use the method of least squares. And similar to whatever we had discussed and a simple linear regression model, a similar procedure is carried out here. And finally, predicted response is written like this. Y cap equal to A cap plus B1 cap x1 plus B2 cap x2 plus etc. plus Bk cap xk. So here, this example is containing 15 weeks time period and pi sales, and then price and advertisement expenditure. So here there are two independent variables, price and this advertising expenditure, and the number of pies those are sold, or we can say pi sales. This is indicated as y. This is the dependent variable. So pi sales is depending on the price as well as this advertising expenditure. So y is a function of x1 and x2. There are two variables here. Okay, let us read this. A distributor of frozen dessert pies wants to evaluate factors which influence the demand. He considers pie sales units per week as the response variable, price in US dollar as one explanatory variable, and advertising expenditure in hundreds of US dollars as another explanatory variable. Data on these three variables are collected for 15 weeks. And fit a regression model to predict pie sales using price and advertising expenditure. Now, carrying on the procedure using the Excel sheet and using data analysis toolpack of MS Excel, the coefficients are calculated like this. Intercept is 306.5 to 61933, and the coefficient for price is this, minus 24.97, and advertising expenditure coefficient is 74.13095,749, and the fitted model is predicted pie sales, that is y, equal to this A value is 306.53. This value 306.5 to 61933 is approximated as 306.53 minus, actually here B1 x1 plus B2 x2, here B1 is negative, minus 24.97, 508952, so it is taken as minus 24.98 into price. Price is our x1, first variable, plus B2 is 74.13, x2 is our second variable, advertising expenditure. So this is our fitted model, y equal to A plus B1 x1 plus B2 x2, and in terms of these pie sales, that is equal to 306.53 minus 24.98 price plus 74.13 advertising expenditure. And the interpretation of regression coefficients is as follows. And pi sales will, now you see this fitted model, pi sales will decrease on an average by 24.98, or roughly 25 pies per week for each $1 increase in the selling price, while advertising expenses are kept fixed. And pie sales will increase on average by 74.13, or roughly 74 pies per week for each $100 increase in advertising, while selling price is kept fixed. That is the interpretation. Here you can see here that as price coefficient is negative, what we say that pie sales will decrease on average by 24.98 numbers, roughly 25 pies per week for each $1. If price is $1, for each $1 increase in the selling price. While if you spend on advertising, then if you spend $100 on advertising as advertising expenses, then the increase in the pie sales will be 74.13 units, roughly 74. That is the meaning here. And a fitted model can be used for prediction purpose. Suppose we wish to predict pie sales in the week when selling price is $5.5 and advertising expenditure is $350. Predicted pie sales in this week, then we substitute those values. That A plus B 1x1, here 5.50 plus 74.13. This is B2 and x2 is 3.5. And when we do this way, we are getting this as 428.62 pies, or roughly 429 pies. So what we have done is we have predicted the pie sales in the week when selling price is $5.5 and advertising expenditure is $350. And here actually this column is in terms of $100, and here 3.3 means it is actually $330. That is why here this $350 is written here as 3.5. So our predicted pie sales is approximately 429 in that particular week, and the selling price is $5.5 and advertising expenditure is $350. Now coming to R square and adjusted R square coefficients, as I said previously that adjusted R square comes into picture in case of multiple linear regression, and it is having no meaning in simple linear regression. Why this adjusted R square coefficient comes into picture, let us understand here. As in simple linear regression analysis, here in multiple linear regression analysis also, we can use coefficient of determination R square to judge the goodness of fit by the same formula. R square equal to SSR by SST, that is 1 minus SSE by SST, where SSR, SSE and SST are obtained using the same formula as discussed earlier. The only difference is in predicting Y values which are given by this equation. In this particular example, that is pie sales and its relation with the price and advertising expenditure, if we calculate R square value, we get this as 0.5215. But one interesting fact is, if we consider fitting a simple linear regression model, taking pie sales as response variable and price only as the explanatory variable, then R square we get as 0.1965. If we put a simple linear regression model taking pie sales as response variable and advertising expenditure as the only explanatory variable, then R square value we get as 0.3095. And what we can observe now, we observe here R square is higher when there are more explanatory variables in the model. This is not just a coincidence, but a property of R square. Whenever an explanatory variable is added to the model, the value of R square increases. This increase is regardless of the contribution of newly added explanatory variable. This is not desired in that way. Thus, the value of R square may be misleading in multiple linear regression models. Therefore, an adjusted value of R square is defined, which is called as adjusted R square, and it is defined as adjusted R square equal to 1 minus SSE by n minus k minus 1 by SST by n minus 1. And adjusted R square increases only if the added explanatory variable contributes in explaining the variation in response variable y. Otherwise, it will not increase. And in this example of this pie sales as a function of price and advertising expenditure, adjusted R square value is 0.4417, whereas our R square value is 0.5215, but adjusted R square is 0.4417. Now coming to the calculation of standard error of the estimate, that is SYX equal to square root of SSE by n minus k minus 1. And if we calculate that, we will get it as 47.4634. Now coming to our assumptions, linearity, independence and homoscedasticity. we can observe here. In figure 14.10, the left side figure represents a nonlinear relationship, while the right side figure represents a linear relationship. Residuals are marked along the y-axis. And in order to examine the independence of errors, we again use the same scatter plot. And in this figure 14.11, the first and the second figures, they represent correlated residuals, while this extreme right side figure shows uncorrelated residuals. And Durbin-Watson statistic can also be obtained to examine the assumption of independence using the Prea formula, which we have already discussed. The assumption of homoscedasticity, that is, all error variances are the same, can also be examined by using the scatter plot of residuals and predicted y-values. In the next figure, left side figure shows a heteroscedastic model. Here, this one. This is a heteroscedastic model, whereas this is a homoscedastic model. And along with these three conditions, we also require the number of observations, small n, to be greater than the number of explanatory variables, k. That is n greater than k. When n is not larger than k, we are not be able to obtain the estimates of regression coefficients, and so we cannot fit the regression model. Now, just like the t-test we used for slope in the case of simple linear regression models, now we discuss t-tests for the slopes here also. Here, null hypothesis is bj equal to 0. That is, no linear relationship between xj and y. Actually, here we test for each explanatory variable xj the null hypothesis. And alternative hypothesis is bj not equal to 0. That is, linear relationship exists between xj and y. Test statistic is given as bj cap by square root of MSC into CJJ, where CJJ is the jjth element of matrix x dash x inverse, and MSC is SSC by n minus k minus 1. Is called as mean squared error or mean sum of squares due to residuals. And now, if we apply this t-test for the problem that pi sales as a function of the price and advertising expenditure, test the hypothesis about individual explanatory variable and suggest if any one of the two explanatory variables should be removed from the model. We use data analysis tool pack of MS Excel, and here this is the output. So intercept, coefficient, price, advertising expenditure, these are the coefficients. That, as I already said, this is A and this is B1 and this 74 is 0.13 is B2. And then standard error, that is already calculated here, 114.25, 10.83, 25.96. Then t-statistic values are calculated, these are here, and then p-values are given here. Here is a printing mistake, here it is 0, no, it is not 0.01, it may be 0.1, 0.19932. In the first column of this table, we are given the explanatory variables. In the second column, we get the least square estimates of intercept, price and advertising expenditure respectively. This third column is giving the standard error. Fourth column, we get computed t-statistics obtained by dividing the least squares estimates by corresponding standard error. Last column provides the p-value, the test of each individual explanatory variable as well as the intercept. And here, if we compare the p-value with some level of significance and reject the null hypothesis if p-value is smaller. Suppose we take p-value as 0.05, that is level of significance 5% and confidence 95%. As in the first case, as this p-value, as I said, here is a printing mistake, it might be 0.19932, and that is more than our considered p-value of 0.05. So therefore, we cannot reject the null hypothesis that the intercept term is 0, because this p-value is corresponding to the intercept. So with here we cannot reject the null hypothesis that the intercept term is 0. Therefore, we may remove the intercept term in the model. That means that the intercept term A can be removed. This can be done by checking constant is 0 checkbox in the regression pop-up window of data analysis toolpack. The p-values corresponding to price and advertising expenditure are both smaller than 0.05. Therefore, at 5% level of significance, we reject the null hypothesis that price is insignificant and advertising expenditure is insignificant in the model. And actually we have observed now that this price and advertising expenditure, they are very much significant, and from this p-value we can ignore that intercept value. So now that means the equation now can be rewritten as that predicted pi sales is equal to this term. Now this is not considered significant. Only this minus 24.98 price plus 74.13 advertising expenditure. So this is applicable now for the prediction of pi sales. What is the question? Let us see. Test the hypothesis about individual explanatory variable and suggest if any one of the two explanatory variables should be removed from the model. That here our answer is that we need not remove those two explanatory variables. Those are very much significant. They need not be removed. Now coming to the F test. In here also we make this hypothesis, that null hypothesis b1 equal to b2 equal to etc. bk is equal to 0. No explanatory variable is significant, and alternative hypothesis is at least one bj not equal to 0. That means at least one explanatory variable affects y linearly. And we proceed in the same manner as we did in case of simple linear regression analysis. And once we make this regression or explained, residual or unexplained, and total, SSR, SSE, SST, and MSR is this SSR by 1, SSE by n minus k minus 1, that is giving this MSE, and this F ratio is calculated by MSR by MSE. And if we go for F test for this example, then we have these values: regression degrees of freedom 2, residual degrees of freedom 12, and total 14, and then here SS values, and here MS values, and F value, and this 6.538607, this is F value, and the significance F, this is actually the P value, and this P value is to be compared with our level of significance 5%, that is 0.05. As 0.012006 is less than 0.05, we can say that at 5% level of significance, we reject the null hypothesis and conclude that at least one explanatory variable has significant linear relationship with response variable, and the fitted linear model is valid. And similar to our computing the confidence interval estimates for the regression coefficients in the simple linear regression analysis, here also we can find out the confidence interval estimates, and the procedure is given here. And you can go through this, and by this I think you have understood what is simple linear regression and what is multiple linear regression. After discussing these regression, simple linear regression as well as multiple linear regression, let us discuss these multivariate analysis techniques. Important methods of factor analysis. Let us discuss here two important methods, the centroid method and the principal components method. There are several methods of factor analysis, but they do not necessarily give same results. As such, factor analysis is not a single unique method, but a set of techniques. Important methods of factor analysis are centroid method, principal components method, maximum likelihood method. Nowadays, for machine learning and other such applications, this method is gaining popularity. Of course, centroid method is also good, but nowadays we can find the use of this principal components method, particularly in machine learning applications. And for that, there are certain terms, basic terms, that is what is a factor, what is factor loading, like that. And we discussed briefly about this. A factor is an underlying dimension that account for several observed variables. There can be one or more factors depending on the nature of the study and the number of variables involved in it. Factor loadings. Factor loadings are those values which explain how closely the variables are related to each one of the factors discovered. They are also known as factor variable correlations. In fact, factor loadings work as key to understanding what the factors mean. It is absolute size of the loadings that is important in the interpretation of a factor. Then there is commonality, h square. Commonality, symbolized as h square, shows how much of each variable is accounted for by the underlying factor taken together. A high value of commonality means that not much of the variable is left over after whatever the factors represent is taken into consideration. And it is worked out in respect of each variable as h square of the ith variable is equal to ith factor loading of factor A whole square plus ith factor loading of factor B whole square plus etc. Then there is eigenvalue, also called latent root. When we take the sum of squared values of factor loadings relating to a factor, then such a sum is referred to as eigenvalue or latent root. Eigenvalue indicates the relative importance of each factor in accounting for the particular set of variables being analyzed. Then we have total sum of squares, and we have rotation, and we have factor scores. All these can be understood by means of examples. Now let us take the first method of factor analysis, that is centroid method of factor analysis. This method of factor analysis developed by L.L. Thurstone was quite frequently used until about 1950, before the advent of large capacity high-speed computers. The centroid method tends to maximize the sum of loadings disregarding signs. It is the method which extracts the largest sum of absolute loadings for each factor in turn. It is defined by linear combinations in which all weights are either +1 or -1. The main merit of this method is that it is relatively simple, can be easily understood, and involves simpler computations. If one understands this method, it becomes easy to understand the mechanics involved in other methods of factor analysis. Various steps are involved in this centroid method of factor analysis. And this method starts with the computation of a matrix of correlations, wherein unities are placed in the diagonal spaces. And here the product moment formula is used for working out the correlation coefficients, but we can use any other method also for finding out the correlation coefficients. And you can go through these steps, but I try to explain all these steps by means of an example. Already I have asked you to go through the illustration 1. I hope you have already gone through, but otherwise also now you can try to understand what is this centroid method used for factor analysis. Now in this illustration, a correlation matrix R is given relating to 8 variables with unities in the diagonal spaces. You can see along the diagonal unities are there. And these are the correlations. In this problem, there are 8 variables, and the relation between 1 and 1, that is 1 only. And the correlation between 1 and 2, that is given as 0.709. You can observe that correlation between 1 and 2 is 0.709, means the correlation between 2 and 1 is also 0.709. That is why this value and this value are same. And you can also observe the correlation between 1 and 3 is 0.204. So the correlation between 3 and 1 is also 0.204. So that way you can understand this correlation matrix. These correlations between two variables, those can be computed using any method. We have already discussed such methods. And in the previous demonstrations also, in simple linear regression model, we have found out the correlation coefficient between x and y. So that is small r. That small r is a correlation coefficient. And similar way you can find out any correlation coefficients, and those are put here. And in this book, the author has used product moment method to find out these correlations. Idea is that we should have a correlations matrix. Okay. Now, using the centroid method of factor analysis, we work out the first and second centroid factors from this information given in the correlation matrix. Now, what we are doing, given correlation matrix R, we have made the column summations. Here column sums. That means 1.000 plus 0.709 plus 0.204 plus etc. That is equal to 3.662. So second column sum, third column sum 3.392, fourth column sum 3.385. Like that we have made the column summations. There are 8 variables, so here 8 summations are there. Now sum of the column sums. That means we have summed up all these column sums, and that is 27.884. Then we have taken the square root of t. That means square root of 27.884, that is equal to 5.281. Then first centroid factor A is calculated as this 3.662 divided by this 5.281. This is our this is the first element of this first centroid factor A. Then the second is 3.263 by 5.281. Then 3.392 by 5.281. So this way it is done. The last one is 3.605 by 5.281. So first centroid factor A, that is now 0.693, 0.618, 0.642, etc. The last one is 0.683. So this is the first centroid factor A considering the 8 variables. Now we can also state this information as under. Here 8 variables are there. Then we are calling factor loadings concerning first centroid factor A. What is this factor loading? What we understand that variable 1, to what extent it is related to the factor A. That means to 69.3% it is related to factor A. And second variable, its relation to the centroid factor A is 0.618. That way we can understand. Here in all these we can find out here particularly 0.694, that is sixth variable. This is more related to this centroid factor A compared to other variables. And now to obtain the second centroid factor B, we first of all develop the first matrix of factor cross product Q1. The Q1, how that is calculated, you please see here. This is the first centroid factor and corresponding to these variables. And these values 0.693 etc. up to 0.683. You can see here 0.693 up to 0.683, and the same here it written in column wise here. And now how this matrix of factor cross product Q1 is obtained, that is like this. The first element 0.480, this is nothing but the multiplication of 0.693 with 0.693, that is 0.480. Then this 0.428 is obtained from the multiplication of 0.693 with 0.618, that is 0.428. Now this 0.445 is actually, that is equal to 0.642 multiplied by 0.693. So that way we have obtained all these values. For your convenience, I simply explain here, last but one element. This 0.464, how it is obtained? Multiplying 0.683 with 0.679, we have got 0.464. And multiplying 0.683 with 0.683, we got 0.466. This is called first matrix of factor cross product Q1. And then we obtain the first matrix of residual coefficient R1 by subtracting Q1 from R. That means this matrix Q1, this is subtracted from this original correlations matrix. Here, this is actually our original correlations matrix, and the same actually here available. So if we subtract Q1 from R, that means this matrix Q1, if these elements are subtracted from that matrix, correlation matrix R, element wise, we obtain this first matrix of residual coefficient R1. This is nothing but our Q1 minus R. Q1 minus R, that is this R1. And we have got these values. For example, our 0.486 is here, 0.486 minus 1, minus 1. So that is given here. Sorry, actually from R this Q1 values are subtracted. That means 1 minus 0.480. 1 minus 0.480, that is 0.420. And similarly, if we take the next one, 0.709 minus 0.428, then we get 0.281. And the third element in the first row, if we take, here it is 0.204 minus 0.445. This is giving us minus 0.241. So that way this residual coefficient matrix R1 is calculated. And now here you can observe the variables 3, here minus sign is there. Similarly for 4 also here minus sign is there. For 6 also minus sign is there, and for 7 also minus sign is there. Then we have to go for reflections. Reflections means in the next matrix we ignore these and we consider all the signs as plus signs only. That is called reflected matrix. And now the reflected matrix of residual coefficients, this is denoted as R1 dash, because this is residual matrix is R1. So when we ignore these minus signs and we write the reflections, that means minus converted to plus, then we have our R1 dash. And here you can observe these minus values, minus 0.241, minus 0.363, minus 0.368, minus 0.316, or any value with minus. All those are written as positive. And now we have taken the column sums, and that means for all these, entire this first column, for second column, third column, fourth, fifth, sixth, seventh, and eighth. So those columns are taken. And then we make the sum of column sums. The summation of all these, that is equal to 20.987. And if you take the square root of this, that is 4.581. So then second centroid factor, that how we have written, that is this 2.580 by 4.581. 2.580 divided by 4.581, and if you do that exercise, then you will get it as this 0.5631. That means here this 0.563 is obtained from this 2.580 divided by this 4.581. This 0.577, this is obtained from this 2.642 divided by 4.581. That way it is done, and finally this 2.718 divided by 4.581, that is 0.593. And now you can observe that these minus signs for this third, fourth, sixth and seventh variables. Obviously here you see in R1 matrix, for third, fourth, sixth and seventh we have the negative values, and then we have prepared the reflected matrix, and we made the column sums, and then the sum of column sums, taking the square root, and we found out the second centroid factor B. After finding out the second centroid factor B, then we are putting this minus sign corresponding to third variable, fourth variable, sixth variable and seventh variable. Now we can write the matrix of factor loadings, that is for centroid factor A already we have written, and now centroid factor B. These values are actually here, these values are written here. So centroid factor B is here. So this is what asked, that finding out the two factors A and B, and so that the behavior of these 8 variables, how they can be explained in terms of these two factors. Now work out the communality and eigenvalues from the final results obtained in this first illustration. Also explain what they indicate. Now coming to this part, what is communality and what we have done here. If you remember, in the beginning I had shown that communality, there is one expression h square. H square of the ith variable is ith factor loading of factor A square plus ith factor loading of factor B square plus etc. And now if we apply that concept here, as there are two factors now, A and B, so h square for the first variable is the factor loading corresponding to this factor A, 0.693 square, plus factor loading corresponding to this factor B, 0.563 whole square. So 0.693 whole square plus 0.563 whole square, this is 0.797. Then for the second variable, the factor loadings are 0.618 and 0.577. So the communality is calculated like this. For all 8 variables, the communality value h square calculated. Now then, what is this eigenvalue? Eigenvalue, this is the variance accounted for, that is the common variance. This is 3.490 for centroid factor A. And how this 3.490 is calculated? It is given in the steps of the procedure. What you can do, this you can square it. 0.693 square plus 0.618 square plus 0.642 square plus 0.641 square plus 0.629 square plus 0.694 square plus 0.679 square plus 0.683 square, and that value is equal to 3.490. Similarly, this column, if these values, you take the squared values and then sum up, that gives you this 2.631. So these are the eigenvalues. Eigenvalue for the centroid factor A is 3.490 and eigenvalue for centroid factor B is 2.631. And this communality that if you make this summation, simple summation of these values, that is 6.121, and even if you make this summation 3.490 plus 2.631, you will get 6.121. So these are the eigenvalues. Variance accounted for, that is common variance. Now what about this proportion of common variance? If we come to this proportion of common variance, the meaning here is here 3.490 divided by the 6.121. So that is 0.57, so 57%. And this 0.43, how we have got? This 2.631 divided by the 6.121, that is this 0.43. And here obviously 6.121 by 6.121, that is 1, so 100%. This is proportion of common variance. Now what about proportion of total variance? Here, as there are 8 variables, the total variance is considered as 8. So as the total number of variables is equal to 8, the total variance is considered as 8. So what is this proportion of total variance? The eigenvalue is 3.490. So the proportion of total variance here means 3.490 divided by 8. That is 0.44, 44%. And here this 0.33%, 0.33 or 33% is actually 2.631 by 8. So that way we are getting here. So then 44% plus 33% to 77%. So what is this 77%? So 77% of the total variance is explained by this centroid factor A and centroid factor B. That is the meaning here. So now here explanation is given accordingly, that the total variance V in the analysis is taken as equal to the number of variables involved on the presumption that variables are standardized. In the present example, V equal to 8.0. So the row labeled eigenvalue or common variance gives the numerical value of that portion of the variance attributed to the factor in the concerning column above it. These are found by summing up the squared values of the corresponding factor loadings. Thus the total value 8 is partitioned into 3.490 as eigenvalue for factor A and 2.631 as eigenvalue for factor B, and the total 6.121 as the sum of eigenvalues for the two factors. This explanation I have already given. The corresponding proportion of the total variance 8 are shown in that next row. There we can notice that 77% is 77% of the total variance related to these two factors A and B. The meaning is approximately 77% of the total variance is common variance, whereas remaining 23% of it is made up of portions unique to individual variables and the techniques used to measure them. And the last row means this. Last row means this proportion of common variance row. What it indicates? It shows that of the common variance approximately 57% is accounted for by factor A and the other 43% by factor B. Thus it can be concluded that the two factors together explain the common variance significantly. This is about the centroid method. So after explaining you how this illustration 1 and illustration 2 are described by the other, now if I show you the steps, then you will understand more easily Because if you read the steps first, in fact you are supposed to read the steps first and then try to understand the illustration. But what I have done is the illustration I have explained you first, and now just to tally whatever we have discussed with the steps given, I am now going to show you those. Yes. This centroid method starts with the computation of a matrix of correlations. This we have done, where unities are placed in the diagonal spaces. And if the correlation matrix so obtained happens to be positive manifold, the centroid method requires that the weights of all variables be +1. If the variables are not weighted, they are simply sum. Okay. But here, please see one thing. In case the correlation matrix is not a positive manifold, then reflections must be made before the first centroid factor is obtained. Reflections means this changing the minus signs into plus signs. The first centroid factor is determined. The sum of the coefficients in each column of the correlation matrix is worked out. This we have done, column sum corresponding to each variable. Then sum of the column sums, that also we have done. Then sum of each column is divided by the square root of t, that also done. And those are called centroid loadings. And the full set of loadings so obtained constitute the first centroid factor A. This also we have seen. Then to obtain the second centroid factor, one must first obtain a matrix of residual coefficients. For that purpose, we have calculated matrix Q1. Then Q1 is subtracted element by element from the original correlation matrix R. And we have got R1. That is the matrix of residual coefficients, R1. After obtaining R1, if there are any minus signs, then we are making the reflected matrix, R1 dash. And in that case, we are changing the minus signs into plus signs. When this is done, that a reflected matrix is done, the loadings are obtained in the usual way, but the loadings of the variables which were reflected must be given negative signs, and that we have seen. At the end, after calculating the factor loadings, we have assigned the negative signs corresponding to centroid factor B. Thus loadings on the second centroid factor are obtained from R1 dash. And for subsequent factors, if we want to find out third centroid factor C, fourth centroid factor D, etc., then the same process is repeated. After the second centroid factor is obtained, then cross products are computed, forming matrix Q2. This is then subtracted from R1, not from R1 dash, resulting in R2. To obtain a third factor C, one should operate on R2 in the same way as on R1. First, sum of the variables would have to be reflected. Reflected means those minus signs converted to plus signs, to maximize the sum of loadings, which would produce R2 dash. Loadings would be computed from R2 dash as they were from R1 dash. Again, it would be necessary to give negative signs to the loadings of variables which were reflected, which would result in third centroid factor C. So I think now you have understood this centroid method. I am making it repeated once again. Here is our correlations matrix, and then we have made the column sums, and the sum of the column sums, then square root of that sum of the column sums, then each column sum is divided by the square root of t, and this is our first centroid factor corresponding to these 8 variables. Actually, these are showing the relationship of the variables with the first centroid factor, that is shown here. Then we have calculated matrix Q1, and here the first centroid factor, the relationships of the variables, those are written here. Then those are multiplied, and this first matrix of factor cross product is obtained. Then this matrix Q1 is subtracted from R. Then we got this R1 matrix. And here some variables, they are corresponding with the negative signs. So we have made the reflected matrix by converting those negative signs to plus signs. Then we have made again the column summations and then sum of column sums and square root of t. Then second centroid factor is calculated. But here we have seen the variables 3rd, 4th, 6th and 7th as they were initially having the negative signs here in R1 matrix. We have put the negative signs here in the second centroid factor corresponding to 3rd, 4th, 6th and 7th variables. Now these two factors are written here. And here what you can understand, the first variable's relationship with the centroid factor b is 0.563. Second variable relation with the centroid factor b is 0.577. And here you can see that here it is negative relation by minus 0.539. Third variable's negative relation with the centroid factor b is calculated here. And similarly fourth one is having negative relation, and similarly 6th and 7th. Then we have seen this communality, that what is the combined relationship of this variable considering both these factors a and b. After finding the communality values, we have found the eigenvalue, that is variance accounted for, that is a common variance. And for centroid factor and for centroid A and for centroid factor B, how we have calculated, this is nothing but that we have squared all these values and summed up. Similarly, we have squared all these values and summed up. Those are given 3.49 and 2.361. This summation is 6.121. And then, as it is variance accounted for, that is common variance. What is the proportion of common variance? That 3.490 by 6.121, that is this, and 2.631 by 6.121, that is this. Then, considering as total number of variables 8, we have taken the total variance as 8. Then, what is the proportion of total variance means? Centroid factor A, that is 3 for its eigenvalue 3.490 by 8, that is 0.44, and here 2.631 by 8, that is 0.33. That is the proportion of total variance corresponding to the centroid factor B. Then the explanation is given below that. One can go through that. So that is the centroid method of factor analysis. Now we consider the principal components method, or simply PC method. This is also called principal components analysis method. And this is developed by Hertling, and it seeks to maximize the sum of squared loadings of each factor extracted in turn. And more importantly, we can see here, this PC factor explains more variance than would be loadings obtained from any other method of factoring. This is an important point, that this principal component factor explains more variance than would the loadings obtained from any other method of factoring. And there are many methods of factor analysis, and out of all those, this principal components method, this is considered to give more explanation about the variance. Now these are the steps involved in the principal components method. And one alternative method is also given here in this book. Alternative method for finding the factor loadings. And here the theory is explained. And as I have done in the previous method, centroid method, here also now I explain you by means of an illustration. Then we can cross check the steps. Now, yes, illustration 3. Take the correlation matrix R for 8 variables of illustration 1 of this chapter, and then compute the first 2 principal component factors, the communality for each variable on the basis of set 2 component factors, the proportion of total variance as well as the proportion of common variance explained by each of the 2 component factors. And here the illustration 1, the same correlations matrix is taken here. And this is continued. Yes, 7 and 8 variables. And column sums, yes. And column sums are given here. But now in this PC method, of course the procedural steps are different. What we have done now, we have calculated a normalizing factor. And this normalizing factor is corresponding to this summation of the squared values of these column sums. 3.662 whole square plus 3.263 square plus 3.392 square plus etc. plus 3.605 square and whole under square root. That is 9.68868. This is the normalizing factor. Then what we have done, or rather what other has done, this 3.662 divided by 9.868, that is this 0.371. And then 3.263 divided by 9.868, that is 0.331. So 3.392 by 9.868, that is 0.344. That way he has normalized this UA1. This column sums he named as UA1. So normalizing UA1, we obtain VA1. VA1 equal to this UA1 by normalizing factor. This normalizing factor is this. So these are the normalized values of UA1. We take it as VA1. Then we obtain UA2 by accumulatively multiplying VA1 row by row into R, and the result comes as under. So here you have to pay your attention. These values of UA2, how these are obtained, please listen carefully. And each element, or I say this 1.296, how this is obtained, let us see. And here it is like this. This 0.371, and these elements, you can see these elements. These are our VA1 elements. What he is saying, accumulatively multiplying VA1 row by row into R. That means we take our correlations matrix, that is here. So 0.371 multiplied by 1.000 plus this 0.709 multiplied by 0.331 plus 0.344 multiplied by 0.204 plus 0.081 multiplied by 0.343 plus 0.337 multiplied by the corresponding element. So that way, here it is fifth one. So 0.626, then plus 0.113 multiplied by 0.372 plus 0.363 multiplied by 0.155 plus 0.774 multiplied by 0.365. This way we have done. This VA1 is multiplied with this first row. And when we have done this exercise, then we have this value, 1.296. By doing all that exercise, we have got this value, 1.296. Now, how this 1.143 is obtained, I explained. This 1.143 is explained like this. This VA1, these elements are multiplied with this second row elements, element by element. Multiplication is done and summed up, and that is giving us this 1.143. Now what about this third one, 1.201? This is obtained from this VA1 values multiplied with the third row third row, element by element multiplied and summed up. Then summation of those multiplied values. That gives us this UA2 third value 1.201 and fourth also 1.201, and let us see. In that case, this VA1 elements multiplied with fourth row, yes, here. This is the fourth row, and this value is also coming as that 1.201. Then 1.165, this is obtained by this VA1 elements multiplication with the fifth row, this row, and then summed up. So by doing that exercise, we have got these UA2 values. For example, the last one, 1.275, is obtained by multiplying these VA1 values with these 8th row values and then summing up. So we have got now UA2 values. Now how we obtain the normalized values? What we do here, similar to the previous, we find out the normalizing factor. Here normalizing factor is, you make just like done here. Now you take these values, UA2 values here, and the square, 1.296 square plus 1.143 square plus 1.201 square plus etc. plus 1.275 square whole under square root. That value is given as 3.493. And after obtaining this normalizing factor, then we have the VA2. We are normalizing this UA2. So normalized UA2 is written as VA2. And this is obtained by 1.296 divided by this 3.493. This is 0.371. And then 1.143 divided by 3.493. This is 0.327. Then 1.201 by 3.493, that is 0.344. Like that it is done. So VA2 values are these. Now what we do, these VA2 values we compare with VA1 values, and whether they are similar or any significant differences are there, we see. Here 0.371, 0.327, and here we have VA1 values here. Okay, VA1 values are here and VA2 values are here, and let us make a comparison. Here first value is same, second value is not, third value is same, fourth value are very close, next is not, next is not, and last is the same, 0.365, 0.365. That way we find they are almost equal, and this shows convergence has occurred. And that means when we are calculating this way, VA2 is compared with VA1, and if those values are more or less matching, then we can think that convergence has occurred. Otherwise we have to go ahead with UA3, VA3, and then VA4, like that if required. And in this case, as there is similarity between VA2 and VA1, VA1 is taken as the characteristic vector VA. Finally, we compute the loadings on the first principal component by multiplying VA by the square root of the number that we obtained for normalizing UA2. What is the number we have obtained for normalizing UA2? That is 3.493. So take the square root of this 3.493, that is 1.868. So what is done now? Characteristic vector VA. These are actually, this is VA1. As VA2 values are similar to VA1, we assumed that convergence has taken place. So characteristic vector VA, we have taken that VA1 as characteristic vector VA. These are our VA1 values multiplied with the normalizing factor of VA2. Then we have got the first principal component 1. So these are the values. That means first variable, its relation with the first principal component is 0.69. And relation of the second variable with the first principal component is 0.62. And similarly, we can explain for other variables. Eighth variable relationship with the principal component 1 is 0.68. Now for calculating principal component 2, we have to proceed on similar lines as stated in the context of obtaining centroid factor B to obtain the following result. Here result for the principal component 2 is directly given by this other, but I explain you how that is done. In this case, what we do, we take these principal component 1 values, 0.69, 0.62, 0.64, 0.64, 0.63, 0.70, 0.68 and 0.68, and similar to that centroid method. Let me go to that centroid method. There I will explain all this. Yes, here we write along this column, we write the principal component 1 values, and similarly here in the horizontal way also we write those values. Then this matrix of factor cross product Q1 is calculated. As I said, the first element here, that will be the multiplication of this element with this element, and the second element of this Q1 matrix is obtained by multiplying this value with this value. So like that, this type of matrix is formed for Q1. Then Q1 is subtracted from correlations matrix R to get the matrix of residual coefficient R1. And after obtaining this R1, we find out any minus signs are there for the variables. If minus signs are there, we convert those into plus signs. And then that is called reflected matrix, R1 dash. Then once that R1 dash is obtained, then we calculate the column sums, and after calculating the column sums, then we go to our principal component method procedure. That will be similar to this. Then here we get column sums, and that column sums we write as UB1, and then we normalize UB1. We have to have this normalizing factor. This normalizing factor, how to calculate, I have already explained. And then each value of UB1 are divided by this normalizing factor. Thereby we get the normalized UB1, that is VB1. We can name that as VB1, and that VB1 values we get here. And then we can obtain UB2 by accumulatively multiplying VB1 row by row into R, and the result comes as under. That is here some UB2 you will be having, and then normalizing that we can get VB2, and then this VB2 can be compared with VB1, and if VB1 and VB2 are similar, then we can assume convergence, and then VB1 can be taken as a characteristic vector VB. Then what we do, that characteristic vector VB, that is VB1, multiplied by the normalizing factor of UB2, that will be square root of normalizing factor of UB2 will be taken here. Then the principal component 2 values can be obtained. The procedure is like that. And here the author has given the principal component 2 values like this. The minus signs are assigned accordingly, and keeping in view of that reflected matrix. And here now we have these variables, principal components, and commonality h square. Commonality h square is calculated just like in centroid method. Is 0.69 square plus 0.57 square, that is 0.801, and like that other values you can see. And then eigenvalue, that is the common variance. That is how this is obtained. and this 0.69 square plus 0.62 square plus 0.64 square plus etc. plus 0.68 square. That means squaring these values and summing up, we get this eigenvalue, that is common variance for the principal component 1, and for the principal component 2. This value is obtained by squaring all these values and then summing up. And this total is equal to 6.0921. Then proportion of common variance, if we calculate, that is 3.4914 by 6.0921. This is 0.73 or 57.3%. And this 2.6007 by 6.0921, that is 0.427, 42.7%, here approximately written as 0.83%. Here it is obviously 1, 6.0921 by 6.0921, 100%. And similarly the proportion of total variance is calculated, and this procedure is given in the text. And all these values can be interpreted in the same manner as stated corresponding to the centroid method of factor analysis. And there is another method known as maximum likelihood method of factor analysis. But once you understand the centroid method and principal component method, and those are sufficient. And in fact, the principal component method is gaining popularity nowadays, particularly in machine learning and image processing, etc. And I hope you are able to understand this multivariate analysis. And please keep in mind that in case of multiple linear regression, we have many independent variables, x1, x2, they can be any number, x1, x2, x3, x4, etc. And the dependent variable is 1, y. That is, y is a function of x1, x2, x3, x4, etc. So that is the problem in multiple linear regression. That type of problems we are dealing with, where there is one dependent variable and many independent variables. In multivariate analysis, particularly here we can say that the number of dependent variables can be more than 1. That means more number of dependent variables. So they can be more than one y. That means y1, y2, y3, y4, etc. And each y is a function of independent variables, x1, x2, x3, x4, etc. There are various methods to solve these multivariate analysis techniques, and some of these I have already covered in the classroom, and there are many other things written like multidimensional scaling, etc. If you are interested, you can go through these. Otherwise, at least to concentrate on centroid method as well as principal components method. And now let us go to the conclusions. But one point here you please observe, in spite of all this, multivariate techniques are expensive and involve laborious computations. As such, their applications in the context of research studies have been accelerated only with the advent of high-speed computers. And here in the questions, what do you mean by multivariate techniques? Explain their significance in the context of research studies. You can answer to this. Write a brief essay on factor analysis, particularly pointing out its merits and limitations. And name the important multivariate techniques and explain the important characteristics of each one of such techniques. Enumerate the steps involved in Thurstone's centroid method of factor analysis. And here, this example, work out the first two centroid factors as well as the first two principal components from the following correlation matrix. I think you can attempt this problem number 6. Here correlations matrix is given, and below this diagonal the elements will be symmetrical. Actually, this is a symmetrical matrix. Here, for example, this element corresponding to 2, 1 will be 0.55 because 1, 2 is 0.55, so 2, 1 will also be 0.55. And 1, 3 is 0.43, so 3, 1 will be 0.43. So, based on this correlations matrix, there are 6 variables. You calculate 2 centroid factors. Here answer is given. You can tally your answers with this. Similarly, you calculate the principal components. Here answers are given. You can carry on the exercise and compare your answers with the answers given in this chapter. And here I want to show you a chart. Here you see. All multivariate methods are some variables dependent. Then if are some variables dependent question mark. If the answer is yes, then dependence methods. How many variables are dependent? If there is one variable dependent, you see we have here multiple regression. Please understand this one. And if there are several variables dependent, then you can see here we have multivariate analysis of variance. And now coming to this side, are some variables dependent? No. That means interdependence methods. Then all inputs metric. Here we have factor analysis and cluster analysis and metric MDS. If it is no, then there are other methods, non-metric MDS, latent structure analysis. And now this point you have to remember. This multiple regression we have covered, and then some introduction is given related to the multivariate analysis and then the factor analysis. And I hope you have understood the multiple linear regression analysis. Before that, simple linear regression. After simple linear regression, multiple linear regression. Then in factor analysis, centroid method and principal components method. And this session I am concluding here. If you have any doubts, then you can contact me either through email or on phone. Thank you very much. We meet in the next session. Thank you.